In the next section, computer calculation of gallery valley flow. This example, they use the shorthand program to write to solve this equation, this problem. Let's go to this problem. Example 11.7, trapezoidal channel. B is equal to 2.5 meter. So B is equal to 2.5 meter. And the side slope is the 0.8, that is the side slope 0.8, has a bottom slope. The upstream portion is 200 meter long, and slope is 0.0 to 0.025, so that is the 20 meter long, and slope is 0.025, and downstream portion is 600 meter long and 0.002. Okay, that is the downstream portion, 0.002, and landing end is 0.012. A discharge is of the 20 cubic meter per second enter at the critical depth from a reservoir at the upstream end. Okay, so we expect that if the critical depth in this point is critical depth is yc, and at downstream end the water depth is 2 meter, so that this point is downstream end is 2 meter. Determine the water surface profile throughout the system, including jump location. Okay, and in this case they use the write the code in shorthand CSO program. Okay, so we just learned how it works, and we can write the program in Excel to solve this problem. The explanation starts from the three separate set of data. I don't show this figure. And the first set of the steep upstream channel has a control depth equal to 0, since it will be automatically assume critical depth in the program. So this is the first portion. That is the first portion, the first set of data. And the second set for the supercritical flow in my channel. It began at the control depth equal to the end depth from the upstream channel, and compute the water surface downstream to the critical depth. So that is the second portion. Okay, and the third set of the calculation the data use the 2 meter downstream depth. So that is this portion start from 2 meter downstream depth as the control depth and compute in the upstream direction. Okay, and below figure show the computation output from the last two data set. The jump is located by finding the position of equal force plus the momentum from the output of the last two data set. Okay. So this gives you the given data for the problem. So landing end is equal to 0.12, and Q is 25. Okay, and slope is okay. So we start from the right. What is the area? That is the bottom bit is equal to 2.5 plus 2 of y. Okay, and area is 1/2 2.5 plus 2.5. is equal to 2.5 plus 0.8 y times y. And for weighted parameter, P is equal to, this one is P is 1.8, and this one should be, okay, square root of 1.64. So weighted parameter is equal to 2.5 plus 0.08. Oh, sorry. One 625. Okay. And for the velocity is equal to Q over A. Okay. And the next, I want to show you how to find the critical depth on this. You can find what is the YC. In this case, if we look at the previous lecture from the lecture number 3, we can find the critical depth from the sat trap. Q times m power 3 over 2 divided by g power 1 over 2 and b 5 over 2. So in this case, if we substitute number in here, modify m is 0.8, 3 over 2. That's clear. So we got about 0.58. Okay, and next we can go back to the lecture number 3. If you look at this, if the horizontal axis is 1, somewhere like here, so 2, 3, 4, 2, 3, 4, 5. No, 2, 3, 4, 5, 2, 3, 4, 5, 6, 2, 3, 4, 5, somewhere here. So we can estimate that the y-axis is about 0.57. 2, 3, 4, 5, okay, 0.57. Okay, we go back to lecture 7. So in this case, you can estimate YC for trapezoidal is okay, so that is where how to get this number, where 1.78 is where it come from. Okay, let's stop for part 1.